Thanks for coming. I appreciate your time. So hopefully you can see my the screen here that says compressor reliability and diagnosis. So
yep, you're good.
Today's class is really sort of a big picture, sort of 30,000 foot view about what causes compressors to fail, and how we can prevent those situations where the compressor is going to fail. We'll talk a little bit more. So this will sort of springboard us into next week with electricity and wiring, because we're going to go over some of the sort of specific diagnosis and sort of how to use your meter to double check those things. So next week will be a partial continuation of this week. So here we are, part 3, our compressor class, and then we, like Nicole said, we sort of wrap things up for the Q1 training next week with a class about electricity and wiring. We'll go over some components and stuff there too. So the objectives of today's class, or of this presentation, is we're going to talk about the role of factors that contribute to the failure of compressors, be that component stress, be it failure modes in the refrigeration system or the electrical system or the compressor lubrication system, which is tied directly into the refrigeration system, right into your refrigerant lines. And then we're also going to talk about how to prevent future compressor failures. So, I mean, if you're working on a system and you've had multiple compressor issues or multiple failures, you've got something larger going on than I keep getting bad compressors, right? That's not your problem. That might be the result, but ultimately the problem isn't, man, I don't know why I keep getting all these bad compressors. So most of the time when we get, oh, you know what? I totally skipped our poll. Can we jump to that? Nicole, do we have a poll for this week?
Yes, we do. It should be up on everybody's screen.
Okay, I'm
so we
sorry.
were going to ask you guys. So the question is, what is your primary role / job function? So PM technician, service technician, installer, or sales? Trying to gauge kind of what you guys are doing.
Yeah, just trying to get a feel of sort of what the audience is today. No wrong answers. And honestly, a lot of you, and I know for me, I was all 4 of these at once, right? So when I was working, there were many times when I did all 4 of these roles in a week, if not sometimes in a day. So you can only pick one. Pick the one that is, I guess, most accurate or closest to what you're doing or what you feel your role is. All right, so mostly service techs. That's what I assumed. I feel like a lot of times the guys on the install side are sort of underrepresented at a lot of classes. I've said this before. I may have said it on last week's class. The good install practices and a good install is probably the most crucial part of gauging the longevity of a system, or how long that system's going to work, or how long it's going to work without breakdowns. There's a lot of things that need to be done right on install to prevent future problems, and we're going to talk a little bit about that today too. So anytime you go out, especially to a service call, if you get out to a call and you're sort of in detective mode, right? I know that I've been guilty a lot of times of trying to solve that problem while I'm in my van or my truck on the way to the call. And sometimes you can waste a lot of time doing that because you sort of convince yourself that you know what the problem is, and you sort of chase your tail for a while before you realize that you need to back up and really look at the data that's presenting itself to you and not what you thought it might be. So that's what we do, right? We get out to a job, we gather information about that job, we take that information and we use that to then take appropriate steps to solve a problem. And sometimes solving that problem is to repair or replace a component. And then we stop there. But there are a lot of times where we need to dig deeper and figure out, hey, not just that I have a failed compressor or that I have a contactor that I need to replace, but why did that component fail? Because if we have larger, more systemic issues, or if we have bigger problems, we're just going to end up replacing those components again. Right. So any HVAC system is made up, it's a sum of its parts, right? So not only do you have the equipment, but you've got the refrigerant lines, you've got the low voltage wiring, you've got the high voltage wiring, you've got the ductwork, you've got the thermostat. So every component can either help that system or make it work longer and last longer, or can hurt it, right? If we have problems with our refrigerant lines, if we have problems with our ductwork, that those can be detrimental to our system and its long life. So this slide says you have two identical units, right? And you can have two identical units. The model numbers are the same. So some of the graphics that you're going to see in this presentation are a little bit dated. Yeah, our units don't look like that anymore. But the information in this presentation is 100% relevant. So you might have two identical units, but the systems are not the same, right? Just because of what I was just talking about. The ductwork is different. The line sets are run differently. There's all sorts of variations from system to system. The indoor and outdoor product could be exactly the same, and the thermostat could be exactly the same, but every system is unique. Even if you have 10 of them on the same street in the same designed house, systems are all unique, and that's something that we gotta consider, right? So you have one that had a failure after 5 weeks, and the other system's running for 2 years. Why is that? Is one of those systems a lemon? No, right? It's probably that there's some other issue on site that's contributing or causing those failures. So that's one of the things we're going to talk about today, right? We're going to take a site survey, and we're going to try to figure out what is causing whatever problem that we're seeing, right? This is something that I hear a lot about ECMs, right? That people keep having to replace indoor fan motors, and a lot of times that has to do with either moisture or airflow or both, right? It's not the motor that's failing, or the motor is failing, but it's because the motor's being caused, or the motor's being broken, right? We're breaking it down. And that leads us into this, right? Stress and system. So every component, doesn't matter what it is designed to be able to handle a certain stress threshold, right? So that stress might be electrical, mechanical, whatever that component is, but there's a certain limit to what that particular component can handle. And then what it will fail at or above, or sometimes below, right? And that's critical to design and engineer, right? Every part or every component is designed and engineered to a particular stress level. So we've got to make sure that when we install systems and or service systems and equipment, that we keep in mind those stress levels, and we want to we want to keep everything operating below those tolerances or below those maximum stress levels so that we don't continue to have component failure. And that stress affects or can be contributed to by a lot of things, right? Wiring, wire terminals, wire nuts, the refrigerant charge, fan blades, windings, fitties, compressors, anything that is a part, right? Because a system is just a sum of all of its parts, right? So anything in that system can be stressed, and if it's overstressed, it can fail. So the typical causes of those component overloads or those component stresses are electrical, mechanical, chemical, thermal, and then shock and vibration, right? And shock and vibration, we can cause systems or components to fail just through transportation, right? And sometimes that transportation is from our manufacturing center to our distribution center. Sometimes that's shock and vibration, or that transportation stress could be from the factory or distribution center to Tropic Supplies warehouse. It could be from their warehouse or resource center to your shop, or to your shop from your shop to the job, etc. So shock and vibration is not only vibration or system shock or from operating. It's also through transportation, or it can be. I've seen many photographs of either refrigerators or condensing units or heat pumps that are set on their side in the back of a truck, right? So we all know, right? When you set that unit, the compressor's bolted to the bottom. If you flip that thing over 90 degrees, you're adding a lot of shock and potential vibration to the base pan of that piece of equipment, whether it's a refrigerator or a heat pump or a condensing unit. So again, if we save a part, we can potentially save a component, and then we can simply potentially save a system or an installation. And again, there's really three systems that we're going to look at to help minimize overloads. That's the refrigeration system, right? So our charge, the electrical system, what kind of voltage and or amperage do we have going to those loads? And then the lubrication system. Are we pulling back the lubricant that compressor needs to properly run? So the refrigeration system, obviously it is critical to the system operation, but it's also critical to the operation of that compressor, because the compressor itself, the windings of that compressor, that motor is cooled by the suction gas. So as we've got our refrigerant coming back into our compressor, that cool suction gas is what cools the windings and the internal mechanisms of that compressor. If our suction gas is overly superheated, or that suction gas is not cool enough, that can cause our compressor to overload. We want to make sure that we pull a good vacuum. So one of the pitfalls, or one of the challenges of doing online classes is you can't really interact as much as I would like to. But when you're pulling a vacuum on your system, anytime you open your refrigeration system, whether it's on install, whether you're replacing an indoor coil, whether you're replacing a filter dryer, whether you're replacing a compressor or a reversing valve or a TXV or anything, if you open that refrigeration system up, you have to pull a vacuum when you close it back in. If you don't pull a good vacuum, there is going to be moisture and or atmospheric gases in the refrigerant lines. They're going to react with the oil and the refrigerant. You're going to create acid, and you're going to fail your compressor. If you don't pull a vacuum, you don't have a micron gauge, and you don't pull a vacuum down to 500 microns, there is still moisture left in that system. I've seen a lot of guys use just their gauges to gauge that they're in a vacuum. That's not good enough. That doesn't tell you how much of a vacuum you're at. I've seen guys purge the system. They're going to blow it out. That does not get all the moisture out. You got to pull a vacuum to 500 microns. How many microns? 500. If you're not doing that, you're going to have compressors fail, especially with 410, because 410 it is what's considered to be hydroscopic, meaning that it sort of absorbs moisture. And as we move into 2025 with new refrigerants, we will see that with these new refrigerants as well. You've got to pull it back. We want to make sure that, and we talked about this last week with superheat and subcooling, right? You want to make sure that you have superheated refrigerant coming out of your coil, your indoor coil, and you want to make sure that you have superheated refrigerant going into your compressor. That way we know that only vapor is going into our compressor. Compressor is a vapor pump, not a liquid pump. If you're have liquid refrigerant going back to your compressor is going to fail for a couple of reasons, right? Number one, it's just not designed to pump liquid. You can't really compress a liquid. You can very minimally, right? But if you're pumping liquid into your compressor, you're putting too much stress on your compressor. The other thing is that liquid is going to pump the lubricant, or it's going to pump the oil out of the sump of your compressor. And now you're going to have that compressor running with no lubricant, and you're going to start to have wear on those bearings, and that's going to cause your compressor to fail. So we want to make sure that we have a good pressure differential across our compressor, right? From our suction side to our liquid side, or our suction pressure to our head pressure. A lot of times, low suction pressure is mistaken for a low charge. Before you, and we talked about this a little bit last week during airflow. Before you hook your gauges up to your system and check the charge, you've got to make sure that your airflow is right. Don't just go out to a system, hook your gauges up, look at the chart, the charging chart, and start putting refrigerant in it. If you do that, you're probably going to overcharge it. If you overcharge the system, you're gonna risk having liquid come back to that compressor, and that compressor is gonna fail. So low suction pressure is often mistaken for a low charge. First, check your airflow. Having insufficient airflow or not enough air through that coil can make your suction pressure low and make you think that you have a charge issue. All right, talked about this already, right? This is what happens when we flood our compressor. Check supply air. For the most popular matchups, and this was one of the quizzes I think we had last week. Most popular matchups, you're going to get that rated indoor airflow from the spec sheet for the outdoor unit. But not all matches are listed there, just the most popular ones. You may have to go to ahridirectory.org to get that. But if you don't have the correct airflow, the charging chart is not accurate, and you're going to end up overcharging your system, and that's going to cause more problems, right? So you got an airflow issue that leads to a charge issue, and now you've got two pretty major problems that are going to cause failure. So a high discharge pressure can be often caused by having your outdoor coil dirty, right? So if we restrict the air that's going through our outdoor coil, it's going to make our discharge pressure go up. It's going to make the compressor heat up. It's going to have us pull higher current on that compressor. Sometimes we might think that because we have a high discharge pressure or a high head pressure that the system's overcharged. So then you pull charge out of it, and then your superheated refrigerant coming back to your compressor is too hot, and we don't cool the windings off enough, and then we could overheat the compressor and open the internal limit on it. So airflow, again, indoor and outdoor, is very important. Every time you go look at a unit, before you hook your gauges up, clean the outdoor coil and check your indoor air. Clearances. So we recommend a minimum of 12-inch clearance around the louvered sides of the unit, 24 inches at the panel, right, and 5 feet discharge air above the unit. So give yourself enough room, obviously, to work on the unit, to pull the panels off, to get around there, to hook your gauges up, to do everything that you need to do. There's been a lot of units that I have seen over the years where it seemed a lot like whoever put it in did not put any thought into how's this going to be serviced or maintained in the future. And sometimes that's not your fault, right? Sometimes you can do everything that you can do. You put your air handler in, and then somebody comes behind you and runs a sprinkler line right in front of the door so you can't get the motor out or whatever. That's nothing you specifically can do about that. But always remember that you're never going to be the last person to come out and look at a system, right? And I think I said it last week. When you leave a job, you're the last heating and air professional to have looked at that job until the next person comes out. But we recommend a minimum of 12 inches from the louvered panels. I'd like to see more. 24 inches minimum from the electrical panel and 5 feet above the unit. Here in the market where I live and worked for many years, there many times I would go out and they would have systems installed under decks with 18 inches of clearance between the top of the unit and the decking. That's going to cause our compressor to fail, right? We're taking that hot discharge air, bouncing it off of the bottom of the decking and sort of recirculating it right back through the coil and the louvers. So your charge and chart, your superheat, and your subcool, your pressures are part of the things that you're going to look at when you're charging. But you also want to make sure, again, that you got good indoor air, and you want to make sure that the ambient indoor temperature is where it needs to be, right? So that charging chart at 95-degree outdoor temp, let's say, is built based on having an indoor temperature between 70 and 80 degrees dry bulb. If it's 90 degrees indoor, you can't really fine tune your charge. You're going to have to let the system run, pull the temp down inside, and then come back and fine tune your charge. If you try to fine tune your charge with your indoor temp that high, you're going to overcharge the unit. So a lot of the stuff I'm just scrolling through because we already talked about it multiple times. So scroll compressors, the newest generation of scroll compressors have sort of, the Copeland scrolls have sort of changed their design a little bit to be more efficient. So the way traditionally that your Copeland scroll worked is that when the suction gas came back in through the suction line into the compressor, there was sort of a diverter that diverted all that suction gas, and if there was any liquid and the oil, down into the sump of that compressor, and then there was a dip tube or a sort of a straw, if you will, that went down and pulled that oil up and any liquid that was in there up into the scroll set. The way that that suction line runs now is that it dumps that suction gas directly into the scroll set. So these compressors are a lot more susceptible to being damaged by liquid than earlier designs were. Why did they change the design? To make them more efficient, right? As the Department of Energy mandates higher and higher minimum efficiency ratings, it's a game of percentages, right? Where we and the component manufacturers have to figure out ways to cut, to increase efficiency. And that's one of the ways that they did that. So a failure mode that you might see on a scroll compressor that you have traditionally hadn't seen in the past is that you might have a scroll compressor that the scroll plates break apart or shear off. And that is because liquid is going back into that compressor. And we should never have liquid flooding back into a compressor, right? Whether by design or by accident, our compressor is not a liquid pump, it's a vapor pump. So if you have experienced that failure mode, it's because that compressor is being asked to compress liquid and you can't compress it. So again, the compressor is cooled by suction gas. We have to make sure that the refrigerant lines are sized properly. The installation manual and the spec sheet both list size, refrigerant size, and length, have sizing and length tables. So they got to be properly sized. The unit's got to be properly charged. Undersized refrigerant lines will reduce capacity. Oversized suction lines can make it so that your refrigerant coming back to the compressor does not have the density that it needs to pull the lubricant back. So if you have an oversized liquid line, if you have an oversized suction line, that can kill your compressor because in many cases it's leaving that oil either in the indoor coil or in the line set somewhere. So it's real important to make sure that both of your lines are sized properly, but on the suction side, if your suction line's too big, you're not going to be able to, the refrigerant, not only the velocity, but the density of that refrigerant is not going to pull the oil back and you'll have compressor failure. If you have got systems that won't keep up or seemingly have reduced capacity, it's very possible that you have got overly superheated refrigerant coming back to your system. The compressor might be running hot. If the compressor is running hot, that can cause the refrigerant to break down. Acid can form that'll etch the bearings. That'll cause compressors to open windings and fail. That can cause vent a pin, and really what that means is that the plug that's plugged into that compressor, one of those compressor pins can fail if acid is present in a system. But overheating the refrigerant isn't the only thing that can create that acid. Not pulling a good vacuum, not pulling a vacuum down to 500 microns can help to create acid, because that moisture or that water that's in the system is going to react with the refrigerant and the oil. That can create acid, and that can also kill your system. Yeah, we all know this. You got to have your systems have to be properly matched, right? Indoor and outdoor, you have to have a matched system. So as we're talking this holistically with the system, right? The whole system, you got to evacuate, pull vacuum down to 500 microns. You got to charge accurately. If your indoor is not moving the right amount of air, or your outdoor is not moving the right amount of air, your charge isn't going to be right. And that the outdoor could not be moving the right amount of air because you have a dirty coil. It could also be because maybe it doesn't have the right fan blade on it. Especially on a system that's been in for a little while, you know, maybe somebody comes in and doesn't puts an aftermarket fan blade on it, or an aftermarket motor. That'll affect the amount of air that's being pulled through that outdoor coil. So moving on to the electrical system, and we're going to talk in depth about this a little bit more next week, but the quality of the system is as important as the voltage. So really what that means is the size of the wire, right? So let's back up. So our line voltage, we've got our breaker panel, right? That feeds our disconnect, or our circuit breaker for the outdoor unit. Then we've got the contactor, and then we've got, specifically as we're talking about the compressor, we've got the capacitor and the compressor. And there may be some other components. If we've got a heat pump, obviously, right? We've got some other components in there, specifically on the low voltage side. But on the low voltage side, we've got our transformer at the indoor unit. That's in a voltage up to our thermostat, which is coming back through to our outdoor unit controls. And all of these components that I just mentioned, right, and everything in between them has a lot to do with the quality of the electrical system. Between the size of the wire nuts, wire connections, etc. Your line voltage going into a single phase outdoor unit needs to be between 197 and 252 volts AC. If it is lower or higher than that, you're going to have issues, and you're going to have component failures. This slide says that your voltage check should start at the central panel. I don't know. In my mind, you check it at your outdoor. If you have a voltage issue there, then you can work backwards and figure out what's happening and where your voltage drop is coming from. And we'll talk about voltage drop next week and what causes it, how to check for it. But if you're running 196 volts, your current is going to be too high, right? So that's going to cause issues. If you're running 260 volts, your voltage is going to be too high for that unit. You're going to overstress those components. On a three-phase compressor, right? So that was single-phase residential that I was talking about, or typically single-phase. On a three-phase compressor, your voltage to each phase or each leg should be somewhere between 187 and 253 volts. And the imbalance, or the difference between all of those three, should be within 3% of the average. And so what does that mean? So you would take voltage on all three legs or all three phases, add that and divide by 3. And then if any one of those is more than 3% away from that, then you have a voltage imbalance that's going to cause you a problem. And sort of the last bullet point here about high voltage causing serious overheating. If you have more than a 5% imbalance, that can cause that compressor to operate at 50% higher temperature than it should, and that is going to cause that compressor to fail. And sometimes what that failure is just a failure of, it's just a failure of that overload, right? So there's a temperature switch or an overload on these compressors. On a single phase compressor, let me go back. On a single phase compressor, I've lost my slide. Anyway, so on a single phase compressor, it's on the common winding. On a three phase compressor, each leg has that overload. And those overloads, as they open and close and open and close, they will eventually fail. So if you're running consistently running a hot or overheated compressor, you can cause an overload to fail, and you can't replace it. So now you got to replace the compressor. Three-phase compressors, obviously we know that three-phase motors, if you have any two of those wires swapped, that can it'll run in reverse. The same thing for a blower motor. So you got a three-phase unit, you need to start it up, make sure that it is operating correctly, hook your gauges up, make sure that you see the pressures, and if it's not, if it's running backwards, you'll know it'll make a horrible racket. Again, I mentioned this earlier, make sure that you don't have a voltage drop or your voltage isn't reduced by any wiring connection, right? A loose wire, a bad wire nut, a terminal that's not properly crimped, and any of that stuff can cause to have a voltage drop, as can incorrect or wire that's too small. If you've got undersized wiring, that's going to cause just like a bad wire nut or a bad connection, that's going to cause higher current, or it's going to cause you a greater amp draw. We're going to talk about contacts and pitted contacts and how to check for that next week. If you're replacing a start capacitor, replace your start relay. If you're replacing a PSC motor, replace the capacitor for that motor. If you're replacing a compressor, replace the capacitor for that compressor. Don't replace a motor that requires a capacitor to run or start and then not replace that capacitor as well. Sometimes you go out to a unit and the compressor won't start, and you put your meter on it. And we'll talk a little bit about this next week. You put your meter on it and you see that the common leg is open, or that if it's a three-phase compressor, you've got a leg that's open. It might be that it overheated. So you might have to wait or come back tomorrow, or just hold off on diagnosing that compressor as having an open winding, because that's what it's going to look like. It could just have an overload that's open. I used to, a lot of times I would run out to if there was a convenience store close by, I'd run out to a store, grab a bag of ice, bring it back to that unit and set it against or on top of the compressor to help it cool off. You know, steel's pretty thick and it takes a while for that compressor to cool off, you know, a few hours, especially if it's in the middle of the summer. Okay, so here's the graphic I was looking for, showing the overload on the common leg of the compressor, not the the common, not the run or the start winding. And so in this, if you were checking between common and run or common and start, they'd both be open if that overload was open. It doesn't mean that the overload won't close again. So give it a few hours before you condemn it and replace the compressor. Then, right, let's say you come back and the overload has closed. Now we got to figure out, why did it open? Because it wasn't a fluke, right? Something caused that overload to open. The compressor's running too hot. We're not getting enough oil back, right? So something caused that. We'll talk about exactly how to check that. And when you do replace that capacitor, you want to make sure that it is rated properly for that unit. There's a lot of times when you go out and you see that a unit has had a dual capacitor replaced, and that capacitor is not the right size for both of those components. It just happened to be whatever that person had in their truck. So you want to make sure that you're using the correct microfarad rating on a capacitor. Don't just replace it with what you have in your truck. On the low voltage side of things, you know, a 24-volt transformer doesn't always put out 24 volts, right? We know this because if your incoming voltage is a little bit high on your primary, then your secondary is going to be a little bit high. If your line voltage is a little bit low on your primary, then your secondary is going to be a little bit low. But sometimes we can have a transformer that's putting out exactly 24 volts when you read it at the transformer. But then when you get out to your piece of equipment, it's putting out, you know, 20 volts. And that's because we're losing voltage along the line somewhere. Again, it could be because we have undersized wire. We could have a wire that's skint. We could have a wire that's cracked. We could have a really long run, right? We could have our low voltage wire could be undersized. 19 volts or less can cause serious problems with our low voltage components, specifically our contactor. We can have contactors chatter, or and that chattering can lead to a pitted contactor. The other thing that it can do is it can cause us to have numerous failures with the coil opening on our contact. As we have lower voltage, our current is going to increase. That increased current causes more heat, and the compressor windings aren't rated for that higher amp draw or that higher amount of heat that they might be experiencing. So if you're having an issue where you've got contactor coils failing, check your voltage. We're going to talk about, like I said, we're going to talk about a lot of this electrical stuff next week. Okay, so lubrication system. Yeah, it is the same system that we're moving refrigerant through. But those refrigerant lines, that line set is doing two things, right? It's carrying the refrigerant that we use to absorb and reject heat, but it's also carrying the lubricant that that helps our the compressor, the internal mechanism of that compressor move freely, right? Just like you can't drive your car or your truck for very long with no oil in it. The same thing happens with your compressor. So line set issues, like I mentioned earlier, if you've got a suction line that's oversized, or if you've got a lot of oil traps, either intentionally or unintentionally, in your refrigerant lines, that can cause the system to not pull the oil back to the compressor. Not having oil washing over those internal parts that are moving in your compressor can add friction and heat. You'll start to wear the bearings. You'll start to wear the scroll plates or the scroll set. Those things can both lead to early failure. Pulling liquid refrigerant back into your compressor can also displace the oil that it's pumping and cause it to not lubricate properly either. Yeah, so I just sort of talked about all this, right? The oil travels through the refrigerant system, and it's the refrigerant, the velocity of the refrigerant is what's pulling that oil back. It's even more critical when the compressor is above the indoor coil, because it's got the system. If you just think about pulling that oil back, it's got to work harder in some ways, and the line set sizing is more crucial, is more critical to make sure that we pull that that liquid oil back up to your compressor. Most modern thermostats have anti-short cycling devices in them that avoid short cycling. So what short cycling is, for those of you that don't know, it's when a system runs for a very short period of time. If a system starts and then immediately stops, a lot of times what's happening is we're pumping a lot of oil out of that crankcase, and we're not giving that oil time to come back. So if we start a system up for a very short period of time, and then we start it back up again, it takes a while for that oil to come back to the compressor, and we leave it out of the crankcase in our suction line or in our liquid line if it's being pumped out, and that can be enough time to kill our compressor. So I've already talked about this, quite a few times. I didn't talk about this one, right? So acid can also be formed if you have what we oftentimes refer to as a burnout, right? And so when you have a burnout, that's what people refer to when I mentioned venting a pin, right? Or your compressor plug or those connections vent or blow out of the side of that compressor, or have a serious arc, and that arc can also create the heat that creates acid in that system. The best way to prevent having to clean that up is to prevent it happening at all. It's very hard to get the acid out of a system once you've had a burnout or you've created acid in that system. So the best way to get rid of that is to have it never happen, right? Let's say it did, and you're trying to clean up the acid out of a system. You've got to flush it. You've got to blow all that out. You've got to put a liquid line dryer and a suction line dryer in it. You've got to run it for 24 hours. You got to come back and replace those dryers, do another acid test. So there's a whole process that you need to undergo when you're trying to get the acid out of a system. It's much easier to prevent it from happening. So we want to make sure we're not flooding liquid back to our compressor. How do we do that? We make sure we have measured superheat at our indoor unit. So when I talk about superheat as it refers to checking your charge, well, we don't really charge by superheat unless you've got a system that has a piston, right? Most of them have a TXV. But it is important to know what that superheat is. And I always like to check superheat at the outlet of my indoor coil, so I know exactly what's happening at my coil. And then I like to check superheat at the outdoor unit, so I know the condition of the refrigerant as it's going into my compressor. Sometimes, depending on where those refrigerant lines are run, how well they're insulated, right? And sometimes that insulation is due to how old they are and how long that line's been in there, and what the condition of that Armaflex or that insulation on the refrigerant line is. But that lets me know if I have any liquid or not, right? If you have superheat, you can't have liquid. So we don't want liquid going back into our compressor. We want to make sure that our suction line is sized appropriately according to our line sizing chart so that we get the oil back to the compressor. And if you happen to suspect that there's oil or you have a burnout, you've got to test for and there's easy So there's very simple way to test for acid, where you use some paper and you just sort of push a little plug or a dimple on that test device on your liquid or suction line, and just a little bit of refrigerant will let you know on that paper whether there's acid present. So in conclusion, don't blame the compressor, right? Do compressors fail? Sure they do. They're any part that's manufactured can fail. But over 40% of the compressors that get shipped back to be sort of autopsied and diagnosed are reported as no fault found. So by the time that compressor gets cut out, shipped back, and evaluated, there's nothing wrong with it. And a lot of times that's simply because there was an overload open, or there was some other component failure and the compressor was condemned. How do we prevent compressor failures? By making sure that we've got proper airflow, we've got proper refrigerant line sizing, we've got proper charge, and that our high and low voltage wiring is good, and that our voltage is in spec. Let's do the 4 quiz questions, and then we'll jump into sort of an open forum. So everybody go ahead and open up your chat window, chat box, and be prepared to answer. First correct answer is going to win it, and you can't win twice.
That is true.
So first question, what method or what is used to cool a residential compressor? So how do we cool the windings on that compressor? All right, so suction gas flowing through the windings. All right, so we use the suction gas to cool the compressor. Number 2, low suction pressure is often misdiagnosed as what? Pretty common, a lot of overcharged units out there. So on a single phase compressor, what do you want to make sure your line voltage is not lower than? What's the lowest voltage that we can safely run our compressor? 197. Way to keep trying. And last question, how deep of a vacuum should you pull anytime you open that refrigeration system? So you open up your line set for any sort of repair, you need to pull a vacuum down to what? 500 microns. How do you know what's 500 microns? Because that's what your micron gauge tells you. Not because I let it run for 30 minutes and I can hear it and I know it's in a vacuum. No, you don't.
Wade, you do have a question here. James Schmidt says, you did not talk about shorted to ground compressor and how to prove that.
All right, so actually, I'll talk about that next week, James, as we go more into the electrical side of things. So I'm sorry, but we will talk about that next week.
Stay tuned. So James, we hope to see you next week.
That's what they call a tease in the radio business.
We got to hook James into the next class. James, we hope we see you next week.